have you here on this webinar hosted by Specim. Thanks, Harry, for that, behind actually the camera. So this webinar is going to be about SWIR hyperspectral camera and seeds. I am Mathieu Marmion, working as a lead field engineer at Specim. And then I'm not alone. I'm really pleased to have a guest with me. So please, Damien, introduce yourself.
Hello, everyone. So my name is Damien Vincke, and I work in the Walloon Agricultural Research Center in hyperspectral imaging, near infrared, in the laboratory, in the field, and topics related to agriculture.
Thanks. So we will be together like hosting this webinar. So basically, the webinar will go as follows. So Harry, can you please put the presentation on so that we can go through the slides? Thank you, Harry. So, I go to the next slide. So yes, welcome introduction. So welcome here. Then we're going to speak about the SWIR hyperspectral camera offering that we are having at Specim, also with the accessories. Then there will be a demonstration which has been pre-recorded, so to avoid any technical issue, with the recording, things like this. And then also a presentation held by Damien and one of his colleagues. Was it Corentin, if I recall well?
Exact, that's correct.
With Corentin. And after that, there will be a Q&A where we will be actually really happy to answer your questions. Before to go into the topics, I would like to remind our audience that there will be some polls where we will be really happy you to answer the question. You don't have to, but we would be really glad about it. So, Harry, can you confirm there would be four polls? How many? 4 polls? Yes, there will be 4 quiz. Yeah, four polls for you. And also, if you have any question, you can write it down already here in the chat. So that after, when we will go for the Q&A, we will answer this question. But please write them down here in the chat, and then we will go through, me and Damien. But I forget to speak. I stopped to speak, sorry, about the context. Now I will speak really about the webinar itself, and I will start to dive into the topics. So quickly about Specim. Specim has been founded in 1995. So it means that last year we were 30 years old. So now we start to be 31. And since 2020, we are part of Konica Minolta. And as you can see, we are having a global presence all around the world, in the United States, also in Europe, like in Germany and Finland, where we have the headquarters, where I am located as well, also in China. And we also have a big network of distributors for all around the world. And since 1995, we have delivered more than 12,000 hyperspectral devices all around the world. So if you think about the topics of today, we are talking, about SWIR hyperspectral camera. In our jargon, SWIR is up to 2,500 nanometers, because for a lot of people in different type of companies, they like to say that SWIR is between 900 and 1,700 nanometers. In our case, we call that NIR. SWIR shortwave infrared is actually up to 2,500 nanometers. And for this specific spectral range, we have actually 2 hyperspectral cameras for that. We have the SX25, and we also have the SWIR, which is the lower one. Both encompass the spectral range between 1,000 and 2,500 nanometers and would be very suitable for the application we are going to speak about. All our cameras, they are line scan devices. So that means that they need accessories to be able to record some data. They record data line by line. And in order to record a hyperspectral cube, you need to have a movement. Either the sample is moving or the camera is moving. So that's why we can offer as accessories some scanners, as you can see here. So the first one, so top one is the 40 by 20. And because, people are speaking know that I'm quite simple-minded, they have to put a name which is easy for me to remember, is because the sample tray is as large as 40 by 20 centimeters. Considering this logic, I think you understand really well what means the lab scanner 100 by 50. It means that this time the sample tray is as large as 100 by 50 centimeters. It is also suitable for different type of camera, including the shortwave infrared and the SX25, which could then be mounted over there. And if you want to work in the field, you have the possibility to put the camera on a rotary platform. Rotary stage, actually, we have 2 models. We have the 10 and the 50. The RS10 can take up to 10 kilos, which could be suitable for the SX25, and also the RS50, which can take up to 50 kilos, which could then be suitable for the short-wave infrared camera, the SWIR one. And basically, the camera is looking sideways, and by rotating like this, you can then take an image outside. By the way, we made a webinar, like, was it last year or 2 years ago, about how to acquire data on the field, and actually we speak a bit more about this accessory over there. Then, just to give a bit of context about seeds and how much it is used in the industry, we know that there is a lot of agricultural research which has been done on seeds, kernel, and plants to understand better how to sort the seeds themselves, if they have a high potential for germination, if there are some disease, or also for breeding plants, also for animal feed, for different type of fungus also, which could be on the seeds. So different type of camera could be used here, the NIR, the SWIR, and the SX25. Just to move on, also to give some background about seeds. Seeds is actually a very important and interesting topic. Germination is crucial. Every time when you buy a package with like seeds in it, you have on it the germination potential. But for some industry, this is really important, especially if you have greenhouses and you want to plant hundreds of thousands of tomatoes, for example. You want to be sure that most of them, they will give you a tomatoes plant. Otherwise, it's a waste of money. So it's important to have like premium seeds. And the price of premium seeds, for example, for a single tomato, it could be up to €1. So here you can certify that with a probability of 95 or 97%, that actually your seed is going to give you a plant. So that's important because if you pay €1, you know that you can get tomatoes, and for each plant you can get about 17 kilos of tomatoes, which is about €17. So you invest one, you get 17. But of course, you need to think about fertilizer, heating the greenhouse, pay your employees and everything. So it's not exactly one for 17, but still to give an idea about the value. And then I started to think like the price per kilo should be really high actually. So I checked on Google what is the weight of tomato seeds. It's between 2 and 4 milligrams. So let's take on average 3. So that means that in every kilo of tomato seeds, you can have 330,000 seeds, meaning about 330,000 euros per kilo. To give a comparison with gold, gold is actually much cheaper. So keep that in mind. Tomato seeds have really, really high value. Tomatoes, but not only. So in that respect, I would like to highlight that we have cameras which could be used to inspect seeds, of course, at the macro level. So you can see like only few pixels on a seed. So you put the camera a bit further away with like a large field of view. But we also have camera where you can see seeds at a microscopic level. So for example, with the FX10, we have the VNIR macro with the pixel size down to 10 micron. You can see the image here on the left-hand side. And on the right-hand side, you can also obtain this kind of macro image with the SX25 and also the SWIR camera. Actually, we call it SWIR 3.0. And you can get here a pixel size of about 20 micron. And already within a seed, you can see like some differences. So for example, as the top one, you can see a green and a blue selection. And below, you can see the average spectrum. And on the blue spectrum, you can see a lot of things. So for example, you can see starch absorption at 2,100 nanometers. You can also see protein absorption after 2,000 nanometers, and also lipids around 1,200, 1,700 nanometers. Also, if you have a high protein content, most likely the reflection will decrease. But anyway, so with these cameras, with those covering the spectral range between 1,000 and 2,500 nanometers, you have the possibility to quantify different parameters which are important in terms of germination potential for later assessment. Anyway, here I would like to have you stay connected with us. Please follow us on LinkedIn. Also, you can go to our website, www.spekim.com. And now actually we are going to have the demo. So the demo which has been recorded, it's about 10 minutes. After that, Damien will have a presentation with his colleague. And after that, we will answer all your questions. So thank you. And now please have a look to the demo. Now to our demo lab. For now, I'm going to demonstrate how to use our system. So you will see I will be using our SX25 on our lab system, and I'm going to measure 3 types of seeds: beans, cucumber, and also tomatoes. So here we are having our demo system. It consists of the SX25, you can see here, mounted on our lab system, the 40x20 scanner. The SX25, it is a camera that we are talking about, which is covering the spectral range between 960 and 2500 nanometers. And it is also a line scan device, so that's why we need to use it on a scanner. So that means it will record data line after line. And here you are obtaining 640 spatial pixels. There are actually 3 lenses available for this camera. We have 66 degrees, 38 degrees, and also the macro lens. And right now it is equipped with a macro lens, which you can see here. And I have another one, which is just here. So the lens itself is about 15 centimeters long. But what matters here is that it's a one-to-one lens with a fixed working distance. It's about 10 centimeters between the lens surface here and where the object are located. So this is actually the distance which is here. We have the samples, which are now on the sample tray, like this. In order to have the 10 centimeters between the lens and the samples, I have the lab jack, like this. Another thing to keep to take into account, to keep in your mind, is that the white reference should be at the same level, or as close as possible at the same level as the samples, which is then here. And we are going to measure seeds of cucumber, tomatoes, and also of beans. It's important to take into account that when you are making measurement with such a high spatial resolution, the depth of field is very narrow. So having flat sample or with a low profile is important. Otherwise, your image will not be on focus for the full sample. So here we have no problem for the cucumber and also the tomato seeds. For the bean, that could be a little bit problematic because they have a certain profile, but this is what it is. Now we are ready to make the data acquisition, so we move to the software. So here we are having Lumo Scanner, which is our software for data acquisition. I just turn it up. First, I will go to the setup. Here we go. Then we can connect the SX25, which is having a GIGI connection, and we are using the Pleura SDK for that. So I just select it and connect the camera. Once the camera is connected, I will look at the serial number of the device to be sure that I'm using the right spectral calibration file. So we have the device 7400021, which is matching with the one of the camera. This is where I'm going to record the data. SX25 as a dataset prefix. Then I will connect with the lab scanner, 40x20, which is the one we are having here. And then finally, I move to the bottom where we have a plugin to also record like this reflectance data, and I would like to have them in floatings. Now here we are seeing our user interface for the data acquisition. So here everything related to the camera parameter, the detector view, the spectral profile, the spatial profile, and here's a waterfall. And everything here to control the movement of the scanner. So first, I will find where the white reference is located. The white reference is located here. I set it as a white start position. Then I try to find the end of it, which is just here, white stop set. Then I will move directly to the tomato seeds. Here we can see the cucumber passing underneath. Whoops, I go a little bit back. So here we have the target start here. Then I go at the end of the tomato seeds, which are just over here, set. Notice that it's already on focus. If I want to adjust the focus, I can just go like this over a tomato seeds. And then I try to find like this if I see some profile either here or here if it is on focus. And I can adjust like this the height, the distance between the lens and the sample. So you can see I'm not on focus anymore. Here I don't see the details anymore, and here it's not that sharp anymore. Then I try to find it again. It's getting better. It's It's getting better, then I missed it. So I need to go back a little bit. And now I am on focus. You can see it here. Now I am using the macro lens. So I need to have a scanning speed which is rather low. So if I make a preview now at that speed, samples are moving, and then we are going to actually go to the target start position, and the tomato seeds are going to be measured. So now we see them appearing like this on the waterfall. You can see the level of the details here, really, really sharp, really, really crisp image. We can see all of them. So now we have our 6 tomato seeds which could be measured, so it was just like a preview. One thing I did not do, I could go again to the white start. I could adjust also the integration time so that I could have like a good signal to noise ratio. Now I am at about 33,000 digital number. It could be a bit higher, but well, I'm still quite happy with that one. I go to the capture, and then here it could be tomatoes SX25 macro, pressing record, and then it will record the data. Since I already have it here, I'll put it number 2. So first it acquires automatically the dark reference, then the white reference, and after that, the data themselves. And the last one, I think, yes, here we are. So now the data have been acquired. We are ready to move with our data processing software called Insight. So it just starts here. Here we go. So now we have Insight, which is here. So as you can see, I have recorded already like before, like for the beans, the cucumber, and also the tomato. This one, it is the one actually number 2, as I was naming. So this one could actually be disregarded. So I can delete it, delete the dataset from disk, and keep like this, like one for each of the tomato seeds. And for example, if I double click here and I want to open the image, we can zoom in the seeds, for example here, and you can see quite a lot of details in terms of resolution on it. So I can make some selection, for example, in this area, also in this area. We can see actually some nice differences depending when you are looking on the seeds, a lot of spectral features as well, and I'm sure Damien is better than me to comment about what they are related to different type of molecule, or to grade the different level of the seeds, because actually you have noticed like when you buy some seeds, there is the potential for germination, which is mentioning behind, for example, 80%, 90%. So here it was for 1 tomato seeds, another one. We can see spectral features which are matching between seeds. And also, if we look at the one acquired with the cucumber, which will open just now, we'll remove this point selection. We can zoom again, make some selection over here, and we can see actually some common spectral feature between the tomato seeds and the cucumber seeds, for example, around 1,200 nanometers. I can remove those one, not to get confused with the tomatoes. So here we have only like this, the cucumber, another one over here, again, some similarity between those 2 seeds. And finally, the one I was mentioning about the beans, where we are saying that this object is rather round, so not all the seeds will be on focus, but some part of it only. Anyway, this is a type of image that you can get. Here you can see the focus was actually really good. We can see even small details at the surface of the seeds. Like here, again, I forgot to make this type of selection. Another type of selection here. Here again. Even if you are not on focus, that doesn't mean that the spectral features are wrong. It's just like if you have something homogeneous, it's okay. If you don't have anything homogeneous, then of course it's making a mixture of everything you are having. So this is for the first one. This is for the second one. We can see here as well some nice images with a lot of details. So as said, for the interpretation of the spectra, I'm not the specialist, and I prefer Damien to speak more about the application itself. All right, so we are back. So then that was it for the demo. Then that's going to be Damien. Yes, Damien is going to be the presentation recorded. So we will look at it, and then we wait for your question and answers.
Okay.
Hello, my name is Damien Vincke, and today I will make a presentation on SWIR hyperspectral imaging with application related to impurities detection and quality assessment of seeds. I work at the Walloon Agricultural Research Center, CRA-W, which is a public research center located in the south of Belgium, in the Walloon region. I work in the research unit called Quality and Authentication of Products. We work on various projects related to precision agriculture, precision livestock, risk management, or the understanding of agricultural products. All these projects are either funded by the EU or the Walloon region. Our research unit is led by our scientific director, Vincent Batten. The unit contains 8 laboratories, each related to a specific analytical technique, such as microscopy, microbiology, near-infrared spectroscopy, and also hyperspectral imaging. Regarding hyperspectral imaging, we have 2 laboratories working on that topic. The MobiLab, led by Philippe Vermeulen, and the DREAM Laboratory, led by Juan Antonio Fernandez-Pierno. One of the main expertise in our research unit is vibrational spectroscopy. It is a research field that Crowe started working more than 40 years ago with the purchase of the first near-infrared spectrometer. You see it here. And since then, our unit acquired many more instruments, either for laboratory, such as benchtop instrument or microscope, but also portable spectrometers and hyperspectral imaging systems. In the case of hyperspectral imaging, it is a research field that our unit started working 20 years ago with the purchase of our first near-infrared hyperspectral camera from Malvern. You can see it here. And, around the same time, our research team was among the founders of the first ESIM conference in 2006. Then, over time, our unit acquired several other imaging systems. And in the picture here, you can see both our systems are equipped with a conveyor belt. This is a key point for us because it allows us to analyze larger quantities of samples and demonstrate potential industrial applications. Our unit has experience with near-infrared hyperspectral imaging on 4 topics, which are process industrial application, authentication and traceability, quality control, and the detection of contaminants, adulterations, and fraud. The last 3 topics will be the focus of my presentation today. The first application I'm going to present is related to contaminant detection in maize. It is based on a collaboration with the team of Paul James Williams from Stellenbosch University in Southern Africa. Paul and his team came to our lab because they wanted to test NIR hyperspectral imaging for the detection of undesirable materials in samples of white maize. They analyzed sound kernels and 13 different types of undesirable material that are considered in South African regulations. This research applied a classification method called partial least square discriminant analysis. The PLSDA models were applied on the spectra following 2 approaches. In the object-wise approach, The models were applied on the average spectrum of each object, while in the pixel-wise approach, the models were applied on the spectra of each individual pixel. In the case of the pixel-wise approach, the results showed a large incidence of errors, which decreased the classification accuracy. On the other hand, the object-wise approach provided the best results with very good accuracy. In addition, the analysis of the spectra indicated that the important wavelengths for the discrimination are related to starch, water, and protein. The next application is related to quality and authentication of cocoa beans. And it is the result of a collaboration with colleagues from Brazil at the University of Pará and the University of Campinas. These colleagues came to our lab to see if it was possible to discriminate the beans of 5 hybrids of cocoa using NIR hyperspectral imaging. Discriminating these hybrids is important because they each have different quality attributes. This research investigated 2 classification methods, PLSDA and support vector machines. Both methods were tested according to 2 classification strategies. The 2-class strategy was based on on 11 models discriminating 2 hybrids, and the 5-class strategy was based on 1 model to discriminate all hybrids. The results showed that the 2-class strategy allowed a good classification of the hybrids and provided a slightly better classification compared to the 5-class strategy. In addition, better predictions were obtained with the average spectrum of a bean instead of its individual pixels. The next 3 applications in this presentation have been made by my colleague Philippe Vermeulen. The first application is related to quality control and fraud detection in durum wheat. This work was made in collaboration with the Barilla company. Durum wheat is the base ingredient for pasta production, but the Italian regulation allows a certain percentage of common wheat. The goal of this work was to use NIR hyperspectral imaging to discriminate between kernels of durum wheat and common wheat. 4 discrimination approaches were investigated to exploit the differences between the kernels of both species, using respectively their morphology, the NIR spectral profile of the kernels, their protein content, and the vitreousness of the kernels. The results showed that each discrimination approach provided a good classification. You can see it here. But better results could be obtained using data fusion to combine the morphological feature of the kernel with their spectral profile. In addition, the analysis of the spectra indicated that the important wavelengths for the discrimination are related to water, fat, and protein. The next application is also about quality control, but in this case, it is related to the use of NIR hyperspectral imaging to assess the quality and homogeneity of pesticide coating on cereal seed. This work used samples of 3 cereal species, either treated by 3 different pesticide formulation with 3 active substances or untreated seeds. In this study, a dichotomous classification was applied with a first model discriminating the cereal species, then a second model discriminated whether the seed was untreated or treated, and a third model to discriminate the 3 active substances. The results showed that it was possible to classify the seed of each species and determine whether they were treated or not. However, it was not possible to have a reliable classification of all active substances. In addition, the result also included the assessment of the quality and homogeneity of the dosage. In this case, NIR hyperspectral imaging provided similar results compared to the reference analysis based on liquid chromatography. The next application is more about fundamental research. In this work, a kernel of barley was sliced at different depths to visualize the variation of spectral signatures and chemical composition in relation to the anatomical structures of the kernel, such as the hull, the germ, and the endosperm. This leads me to the last application of this presentation, which is related to the demonstration of our hyperspectral system for purity assessment in samples of faba bean. This work uses a dichotomous approach to detect various foreign bodies in the sample and assess its level of purity. In addition, this work showed characteristic spectral response beyond 2000 nanometers, relevant for the discrimination based on lipids, starch, or protein content. The research was made by my colleague Corentin de Moitié, and he will present the demonstration of the system in a short video.
Hi, welcome in our hyperspectral imaging lab at the Walloon Agricultural Research Center in Gembloux, Belgium. My name is Corentin de Moitié, and I am here to present you our latest custom-built acquisition setup that we use with the SWIR Specim system. This setup includes a conveyor belt and is ideal for a broad range of application. But in our case, we mostly use it for the analysis of agri-food products. It replicates at a smaller scale what the industry might need for batch quality control. The Specim SWIR system is a line scan, high-speed, shortwave infrared hyperspectral camera that operates in the spectral range from 1000 to 2500 nanometers. It has 384 spatial pixels and a high signal-to-noise ratio, ensuring quality measurement. The conveyor belt allows for the continuous flow of samples underneath the camera, ideal for batch quality control. It is made of a dark and resistant material that can be easily cropped out during data treatment. This system is equipped with 8 halogen light bulbs for optimal illumination of the measurement area. The camera and the conveyor can be both controlled through a software allowing for acquisition, data treatment, and real-time prediction. A macro lens can be added to the camera to capture the finest details. Moreover, the height of the camera can be easily adjusted, and the whole system is mounted on wheels, making it easy to move around. You are now going to see a demonstration of the purity assessment of a faba bean batch. The conveyor belt allows for the continuous flow of samples underneath the camera. This method was developed to detect several impurities in faba beans, including insects, plastic particles, pebbles, straw, and so on. The camera has been turned on and is connected to the belt. A white and a dark reference have already been measured. The system is now ready for analysis. Post-analysis data treatment can also be performed on the acquired image for the implementation of specific models. The characteristic spectral feature above 2000 nanometers are especially interesting for discrimination based on lipids, starch, and protein content. The SWIR system coupled with the conveyor belt allowed for the development of highly accurate quantitative and qualitative models based on a large amount of samples for quality control. The setup is good as it is, but we would like to still add some improvement, notably by adding a sorting system at the end of the conveyor belt, and also to enclose the measurement area for to avoid any external disturbances. I would like to thank you for listening to my presentation, and I wish you a lot of success in your hyperspectral journey.
This concludes
right.
our presentation. In the name of all my colleagues, I thank you for your attention, and I also thank Specim for giving us the opportunity of presenting our work. And I would like to mention that we will organize in March a training course on vibrational spectroscopy and chemometrics, which will include several sessions on hyperspectral imaging. For those who are interested, you can scan the QR code, or you can also send me an email. Thank you for your attention.
Sorry, I was too quick. I was jumping while you were still like talking, like Damien. Hey, Damien, by the way, you forgot to mention something, like in 2 to 3 years, what will happen?
Yeah, so our research team is going to organize the next near infrared conference, International NIRS conference, and it will be in Brussels. So yeah, it will be, I think, in 2029, if I'm not mistaken.
I will still be working. I know.
Yeah, well, me too. That's for sure.
All right, so thanks a lot. So now we have been going through the presentation of the company, also our products, then demonstration of how to use our camera, and finally, I mean, like the presentation from our guest speakers, like you, Damien, and also Corentin. Now we are going to answer the questions. So please write your question in the chat. Yes, it's possible to see actually those questions. Like there is like those triangle with three bars where it's possible to focus on the questions only. Anyway, so how deep does the light penetrate? This one. Yes, how did the light penetrate? Do you want to answer here, Damien, or should I? It's for you.
Yeah, I can answer that. It's just a few microns. It doesn't penetrate a lot. Actually, we published an article where we were able to show that we were able to detect kernels inside heads of wheat in the laboratory, but the technique itself doesn't penetrate very deep. Maybe you can add a few points on that, Mathieu?
No, I agree with you. Typically, hyperspectral imaging is a surface inspection method, first of all. So it's not like X-ray, which we'll see through. Then I agree, it's like few microns, maybe 100 of micron, but that would be the maximum. So yes, no, I don't have more to say here. All right. So the next question. So what can you say about illumination source? I can take that one. So about illuminations, it depends, of course, on the spectral range we are talking about. But if we are talking about shortwave infrared, to the best of my knowledge, I don't know anything better than halogens at the date of today. Of course, there are some developments which have been made about LEDs, hyperspectral LEDs, but typically they go between 900 and 1800 nanometers, or then between 1100, 2200 nanometers, but to cover really the full spectral range between 1000 and 2500 nanometers, I do not know anything better than halogen. We have tested as well, by the way, supercontinuum laser, but it went up to 2350 nanometers. So again, the last 150 nanometers were missing. So I would say halogen, if you're outside, of course, the sun is always a good source of light, but you cannot have it in your lab. So next question, please. Damien, that's for you. There is your name on it.
Yeah, I see that. So let me read it, because so
Okay,
in the corn classification example, you mentioned that you compare pixel-wise classification with object-wise classification based on average spectra. Given the large spatial variation across a seed, I would expect that averaging throws away some information. Do you know of object classification methods that also incorporate spatial information? That's a very good question. I actually, like, out of the top of my mind, I don't know method that allows to do that. But I know that with deep learning methods, you can combine very well morphological features. And it's also, deep learning is a topic that we study that we start studying in our research unit, mainly my colleague Antoine Derek. But yeah, sorry, I'm not able to give a lot more information on that one.
that's okay. We cannot know everything, you know. So, how much not flat sample surface could badly affect classification? So then it actually raised quite a lot of questions here. The first question that it raised, it's about the depth of field. So that's true that when you are making macro measurements, because of the small pixel size, of course you could have a big F number, but still you have a depth of field which is quite shallow. So you could see, for example, on the record, on the beans, you had only some part of the sample which was on focus, but not the rest. If you would have a length that you would be further away and you would have bigger pixel, then you would have depth of field, which is actually much larger. But then to answer your question, how much it affects, let's say that the spectral signature is the same if you are blurry or if you are not blurry. But it's just like you may have a mixture. So, for example, if you have two things next to each other, if you make something blurry, it means that actually it's going to be the spectral signature of the blurry pixel is going to be a mixture of the two compounds that you are having. If you have something which is really homogeneous but it's blurry, it doesn't matter. Only on the edge it's going to be, a bit problematic because you will not have a sharp differentiation between the background and your sample. But this is the way you need to understand it. Okay. The next question: how do you know which bands they belong to? The bands of protein, lipid. Do you have any reference page or website where you can look up the bands and wavelengths? Any library available? Do you want to answer, Damien?
Yeah, I can answer. So there's a lot of literature on that, and there's a reference book. For example, in agriculture, we have a series of books which, like, you have tables, and it will tell you, okay, that wavelength, these nanometers, it's related to this chemical bond, which is typical of this type of molecule. And so yeah, if you want, I can Pole, you can send me an email and I can give you a reference related to that with pleasure.
Yeah, this is true. So you can look at libraries like this, but I have to say very often it's also, you know it because you have been looking for it quite often.
Yes.
So you learn it at the end. But
yeah. By the time you get used to, like, you see a spectra and you know, this is probably,
This I know. Yes.
I've seen this before.
Then the next question: can one do a research visit in your facilities with our samples? Interested in faba beans and cereal. I believe this is for you here, like
I
Damien.
guess so. Yes,
Yeah.
you're very welcome to, and this is valid for everyone who is attending this webinar. As you could see in our presentation, we have a lot of collaboration with other institutes all over the world, and we are always very happy to have scientists coming and having nice discussions, discovering new topics.
Then the next question is like, have you had experience using HSI to detect seed viability? Well, I can try to answer. So yes, we have had customers actually using our cameras for this type of application. So yes, it's possible. So it could be FX17, it could be the shortwave infrared, SX25. Those are the cameras which could be used for that. Will you consider making a specking camera in the UV range, 200 nanometers to 400 nanometers? That's a good question. But I have to say, we know we have competitors here. Hello. So we are not going to speak about our roadmap in details here, but please contact us. You know, I am Mathieu Marmion, so mathieu.marmion@specim.com. And then we can give you more details about what we are planning to launch, to develop, and things like this. But I'm not going to say it here online. I think you understand me. Can you give us an idea of how quickly a conveyor belt can pass beneath the camera while still capturing spectral data effectively? Do you want to answer here in the context of seeds? Maybe I can answer in a more general context after. So Damien, can you? Yeah.
Yeah, actually, it can go pretty fast. In the past, we did a research related to ergot bodies in wheat. I don't exactly have the exact numbers in mind, but I think it was like something like 30 kilos in an hour. I'm not sure. I don't want to say incorrect answers, but it can be pretty fast. And I think, Mathieu, you're going also to mention maybe removing some weaknesses.
So basically the thing is like, well, the technology is push-broom. So you need to have a movement. That's the first thing. It's mandatory. You need to have a movement in order to reconstruct your hyperspectral cube. Then there are some applications which require speed. For example, when you're in the recycling industry, you could have a conveyor belt and you could have, the plastic passing like this under the camera. And we have seen conveyor belt up to 2-3 meters per second. Of course, you need to consider that during the acquisition time, the sample is moving. So it may induce a little bit of a blur as well. So you need to make a combination of your pixel size, also what is your integration time, and also what is the speed of the belt. So when you combine everything, actually, you really know what your camera is actually seeing. And actually, I invite you to look at our website. We have made a technical note about what your camera actually sees. So there it explains also things about speed, width of the line, and things like this. Okay. What is the typical limit of detection of contaminant, knowing it can vary from the contaminant and the matrix they are in? Do you want to speak here, Damien?
Yeah, I can provide some answers to that question. So one key factor to take into account is, for example, if you are analyzing a batch of kernels, you can, if you're able to detect one kernel in like thousands or billion, that's fine. But if, for example, you work in powders and you have mixtures where you cannot distinguish the different objects, then I would say with near infrared below 1%, it starts to get really tricky.
Yeah, and then I would add as well, in terms of spatial resolution, I like to have at least 3 pixels to detect an object. That's one thing.
Yeah.
Then we are stuck. Harry, next question. Oof, it's coming. So yeah, that was a question about the typical cost of an FX25. No, we are not going to answer about cost here. Then, yeah, thank you very much for the presentation. Can you elaborate on the MTTF of the SX25? I see it is still in cool. Do you know how many hours the cooler can work before maintenance failure? Okay, so about the MTTF, it is about 25,000 hours. Then, of course, it is a Stirling cooled. So this is a way that you can get like a detector sensitive down to the cryogenic level. And then about, yeah, I see. Yes, that's what I can say. So of course, there will be a need for maintenance, especially if you use it like 24/7. But this is something we can work on a contract base. Alors, would it be possible to measure the moisture or moisture content in metallic material? Whoa. So, moisture content, yes, that it's possible to do it in different type of material, because I think, Damien, you made some paper showing that there are some absorption around 1,400 nanometers, even 1,200 nanometers. So it's possible to make quantitative analysis here. But then moisture content in metallic material, that's a bit tricky, because I know that, for example, if you consider rust as being one of the elements, I know it could be monitored, these kind of things. But moisture content in metallic materials, that myself, I haven't seen. The question for me is, there is also my name here. How did you make a proper line light profile from the super continuum laser? That's a good point. That's true that from the super continuum laser, you were getting only a point. So then we had to put a diffractive like optics. So actually we could get a line. But you have to consider that, for example, you had a certain spectrum at the middle, but on the edge, it was a little bit different, something to take into account. But here, luckily, I had to help with me, like the optical designer at Specim, to transform this point on a line, and then we could make actually the research, the measurements. In pixel level models, is any pixel counting strategy employed to assign a sample to a specific class? Do you want to answer here, Damien?
Yeah, I can answer. So yes, you can also use that strategy to give you a prediction, like a threshold decision to say, okay, this is fababine, this is impurity, for example. So yeah, maybe you can also add something.
Oh, well, I don't have more to add. So does the industry have the infrastructure to utilize this developed method, for example, to sort seeds of different quality grades? And does the industry have pricing mechanism in place for these different quality categories? Yes and yes. Actually, seeds for us is quite an important market. We are selling quite a lot of devices exclusively for this market. So yes, the industry is actually looking at seeds to grade them. Because as I say, when you go to the shop, typically the germination potential, when you buy seed, it's about tomato, it's about 75, 80%. It's not much. But if you buy like hundreds of thousands of seeds, you want to get 95 or 97%, even more. So then, yeah, there is a mechanism like this to sort the seeds and grade them. At wavelengths above 2000 nanometers, reflectance intensity decrease and detector noise typically increase. If a polarization filter is added to the imaging system, how is the SNR expected to change in this region, and would any SNR improvement be uniform across the spectrum? I think it's a question for me, or do you want to jump in it, or it's maybe more like
No,
I can jump in it. Okay.
Yes.
Well, you are right. Typically, the sensors, they are less sensitive when you go above 2000 nanometers. But by the way, that depends on the detector. There are some which are better in some higher wavelengths. So for example, some MCT, they could be better in some higher wavelengths. Our FX50, which is between 2.7 and 5.3 micrometers, is based on the MCT detector, like the SWIR camera. It's just like different temperature, different mixtures, first of all. Secondly, if you have something which is not balanced, I will not use a polarized filter, but I will use what we call a spectral flattening filter. So basically, a spectral flattening filter, it is a filter which transmission curve is at the opposite of the sensitivity of the camera. So for example, if you have the sensitivity, which is like this. Then you could have a filter, which is the opposite. When you put them together, then in kind somehow compensate. But when you do that, you will limit as well the speed because you have less light entering the system. So yeah, there are possibilities to do that. But then will it be uniform? No, it will not be completely uniform either. If we only measure a few micrometers into the material, is the energy source limiting? In other words, could a more powerful energy source generate more information further below the surface as the material is excited at greater depths? Do you want to answer that one, Damien?
I can provide an answer. I would probably need your confirmation also. I think you can put more light, but I don't think it's going to change much.
It will not change much.
Yeah.
The only thing you could think about is working in transmission. So for example, you could have the light underneath, then you can have the sample and the camera at the top. But to be able to do that, you need to have a lot of light. On seeds, they are quite thin. So for example, tomatoes, you will be able to have some transmission measurements, but this is not working for everything. So now you have to keep in mind that hyperspectral imaging is a surface inspection method. Can you use this equipment for a quick estimation of food composition? Are there built-in standard curves, or can someone create such a curve using sample of known composition for estimating the composition of fruit, vegetable, or meat with regard to total protein, total sugar, fiber, lipid, water, vitamin C content, or similar parameters? Also, has the equipment been used for estimation of microbial load of food, for instance, presence of fungi or bacterial biofilm on the surface of food materials? That's a long question with a lot of questions, actually. So, can you use this equipment for a quick estimation of food composition? Yes, our cameras have been used for the food industry to detect contaminant. That's one thing, but also to grade the food. So you can measure the moisture, the protein content, and also the fat content. So we have actually on our website some feasibility studies showing these kind of things. Then for the fruits, the vegetables, there are also parameters which could be detected. For example, the ripeness, the sugar content, which is a Brix index. That can be done as well with a hyperspectral camera, and it is used in the industry for that. The microbial load, that's more tricky because it could be in a really small let's say concentration or small quantity, which makes it very difficult to be detected. We have customer claiming they can do it, so I believe it's possible to do it. Myself, I always had issue, but fungi, actually, you, Damien, you were showing like fungi on the corn kernel, so yes, there are possibility. So yes, for the food industry, there are a lot of possibilities here. So, hi, for Bart. So I don't remember what was the Bart question, but this is a topic I'm currently investing at the CRA. So if you have an application where spatial information matter and which to discuss, you can, okay, so actually it was not really the question, it was an answer. Sorry. Did Specim develop all of the software shown today? In the Specim demonstration, when it was the inside software, yes. But you are using also another software, you, Damien, so you're not using inside, you are using another one. So maybe you can speak about this one as well.
Yes, we also use the software from the company Predictera.
Breeze.
Breeze, yes, exact. But we also use the Lumo software for other cameras from Specim that we have. So for the image acquisition, we use different softwares.
Yeah, there are a lot of possibilities. For example, our data, they could be open in Python, MATLAB. There are,
exactly,
many software. But yes, the one showing first with my demo, it was Specim based. Damien, that's your question, obviously. Does your lab publish any publication-specific hyperspectral benchmark dataset based on the research you presented today? Additionally, do you provide open access reference spectra for different seeds varieties to support classification and quality analysis? Damien, your name is written in the question.
Yes. So, do we provide application-specific hyperspectral benchmark dataset based on our on the research we presented? We do not provide like publicly these data, but if you're interested in exchange of data, we can of course always talk about it, and depending on the project where it comes from, because sometimes we also have collaborations with industries. So in that case, it might not be possible, but yes, we're always open to share our data. And then the next question is, provide open access reference spectra for different seed variety. Yeah, again, same answer. We don't provide open access spectra, but we have a lot of spectral libraries, either from hyperspectral equipment, but also from conventional spectrometers. And we have a huge database, but we don't share it. But in the case of collaboration, it's always possible. But to my knowledge, it's not open access so far.
Thank you. Is it possible to do hyperspectral imaging of powdered samples? And can we check the level of oxidation in powder samples? Powder samples, yes, that's not a problem. We have measured a lot of powders. That's not an issue at all. Then the level of oxidation, you mean the level of transformation due to exposition to the air, to the oxygen? Yes, if the spectral features are changing because of the oxidation, yes, it's possible. If the spectral features are not changing, well, then you cannot see it. I work in Chile with HSI, and I will be going to Belgium in a few weeks. First, I would say it's a good idea. Will it be possible to visit your facilities?
Of course, you're welcome. Send us an email and we can arrange something.
What is the most unexpected use of your camera, of your equipment, sorry, you have discovered recently? And has this discovery led to product improvement? The most unexpected use of your equipment. I have to say we had some ghost hunters sometimes, but it did not lead to any improvement, I have to admit. But just like this, no, typically when we develop a camera, it's not based on a single use case. So we try to understand if there is a market behind things like this. So the unexpected use case, they are not that common, I must say. There are always some cases you feel, yeah, okay, that's interesting. I did not think about it, but no, doesn't come to my mind here. Do you have anything developed that align a linear RGB camera and a linear hyperspectral camera? I think you want to contact us. So please send us an email, and I think we will be able to talk. Any experience in microplastics classification, size, measurements? We have worked on it. Damien, have you worked on microplastic or not at all?
On hyperspectral imaging, no. With spectroscopy, yes. But
okay. On hyperspectral imaging, we did. Actually, we have made a case study on our website about microplastics. So I'm sure that Harry will be happy to share the link. It's already in the chat. So you see, I'm already late. So basically, yes. Keep in mind that you remember I was talking, we are having the macro lens where you can have a pixel size which is about 20 microns. So I'm used to say that if you want to detect one of the plastics, you need to have 3 pixels. Theoretically, 2 pixels is enough, but I prefer 3 because then you are sure to have at least one big pixel as the middle, which is not a mixture of the background and the plastics. And so that means like typically 50, 60 micron is the minimum size that we can really detect, and then it could be identified as well. So yes, we have had actually quite a lot of research done about microplastics. Coming back on the software, any advice on the usage of open source solution, Python libraries, to process HSI cube? Well, our data, they are not only Specim data, they are saved in the NV data type, which is compatible basically with MATLAB, with Python. I don't remember the name of the function that our users they use in Python, but at least in MATLAB it was multiband read, for example. Yes, you seem to use MATLAB and Python yourself, Damien. Maybe you can say something here.
Yeah, so I use mainly MATLAB, but we're also getting into Python. There are some libraries related to that. But yeah, as I said, I don't really work in Python. I should ask my colleague Antoine Dereyck. He knows better about that.
Which spectral range is best for honey adulteration detection? But first of all, I will not use a hyperspectral camera for that, but I would use a B. But then if I don't have a B, then I would use maybe a VNIR camera between 400 and 1000 nanometers, probably because, sugar, when it is crystallized, you have an absorption peak at 985 nanometers. So if this peak at 995 nanometers could be monitored in order to check the adulteration of the honey, I will go towards that. So there is the sugar at 985. There is another one around 1415, if I recall well, or 1480 for the sugar. So I will look at those ones. Can I use the sun as a light source for imaging kernel on spikes heads with near SWIR camera in field condition? If yes, what data processing or filters I should use to do, I should use due to instability of sunlight. Can you give, because I know you are using hyperspectral camera on the field as well, Damien, if I recall well.
Yeah.
Can you explain how you use the sunlight, if it's a problem, what to take into account?
So my first recommendation would be to make sure to always work with sunlight without any clouds in the area.
Yeah, because it's like a water filter. It's
Yes.
like a water filter between your light source and your sample. You don't want that.
Exactly. And then you can apply pre-processing, like normalization for the of the spectra. You can do SNVs, autoscale. You can apply derivatives. But the question is, I should use due to instability of sunlight. I would say if you measure outside, I would recommend to always measure between around the noon time. And this way you avoid changes in solar intensity. Of course, there's seasonal variations, but yeah, that would be my main recommendation, I think.
Yeah. No, but I think it's fine. Yeah.
Yeah.
Is it possible to do hyperspectral imaging of leafy vegetable in the SWIR range? How will leaf heterogeneity and water absorption band affect biochemical analysis? Well, that's a good point. So I wonder if actually, if you want to look at salads, for example, if you want to use this for something else, I really wonder if actually the good spectral range is not between 400 and 1000 nanometers. Because when you have leaf, you have chlorophyll, and you want to monitor like maybe the chlorophyll content and things like this, so it might be wiser to move between 400 and 1000 nanometers. That would be actually my first recommendation here. Have you ever used your product for mining application, drill core scanning? Oh yes, we have a product for that, which is called the CISO Rock, and we have the possibility to measure drill core. We have a platform dedicated for that. with 4 hyperspectral cameras. At the top of that, you could have 3D sensors. Then it's possible to have as well like high resolution RGB cameras. So yes, for grid core analysis, we are actually a really good partner and supplier for this kind of thing. So yes, it's possible. Okay, then Spectral Pi is one library. Orange is a data analysis tool based on block, very powerful, integrated with Python, all open source and very powerful. That's not a question, but thanks for giving this kind of advice to our audience. Thanks, Harry. And HSI for all sorting. Yes, so apparently Harry has been posting like the link for the CISO rock, I can imagine. And HSI for all sorting. By the way, you should go to our website, and there, if you go to the application division, there is actually a table which has been provided by one of our partner, TerraCore, which explain which OR can be separated, which hyperspectral camera, which spectral range. So actually, I invite you to visit this site. It seems that we don't have any question now. So how is it possible? No question anymore. So I will give it still half a minute, maybe. Well, if not, I think I just have to thank everyone, and especially you, Damien. I mean, thank you very much for being here.
Thank you to you and Specim also. It was really nice.
Yeah, thank you. Thank you for being here. I would like to thank all our attendees for this webinar. It was a pleasure to be here with you. So you can stay with us by following us on LinkedIn. As you can see here, you can see our nanobot, who will be really happy to give you some advices as well with his single eye, but what an eye. And yes, so we are really delighted to be here. And if you have any question, please do not hesitate to drop any message. Thank you very much. And I wish you to have a nice day, evening, night, whatever, wherever you are located. Thank you.
Thank you. Bye.